Good evening, guys. This is Apiram, and a very warm welcome to today's seminar titled "The Idea Factory: How Bell Labs Invented the Future." Right. So, in this seminar, we'll be looking at how Bell Labs shaped the future that we live in today, with some of its world-changing innovations over the past 90 years, ever since it was founded in 1925. So, first, let's look at the flow of the seminar. So, first, I'll be telling you how Bell Labs was born. Then, we'll be looking at a timeline of its innovations. Then, Bell Labs' recipe for success, its legacy, how the fall of Bell Labs happened, and the current research work that is going on at Bell Labs. Right. Bell Labs was very commonly known as the idea factory or the crown jewel. And for most of the 20th century, it was the most innovative scientific organization in the world, right? And be the first ever transistor, the first silicon solar cell, the first ever laser, or the first communication satellite. It has been involved in nearly every technological milestone in the last 9 decades. And although not all of these elements were invented at Bell Labs, it was only at Bell Labs that they were actually brought to maturity. And for the work done at Bell Labs, a total of 9 Nobel Prizes and 5 Turing Prizes have been awarded. The researchers at Bell Labs believed that they weren't really working in a laboratory, but they were indeed working in an institute of creative technology. And this was as quoted by one of the Bell Labs then directors, Mervyn Kelly, where there wasn't necessarily a distinction between art and science, right? So Mervyn Kelly saw research as some sort of a work where you had to be really innovative and creative, and he also saw research as a non-scheduled area of work, where there were no particular deadlines or no progress reports. And it was always believed that, the researchers at Bell Labs always passed all of their deadlines without actually having any deadlines. And also another question which we'll be looking at in this seminar is how exactly did Bell Labs create the future that we live in today? We've seen that it has created the future and shaped the future in a lot of ways, but how exactly did it do that? So, looking at this picture, this is the first ever transistor that was developed in 1947 by William Shockley's team. And for the same, William Shockley got the Nobel Prize in 1956 along with Bardeen and Bretain. Now, looking at the birth of Bell Labs, origins of Bell Labs, date back to late 1870s when Alexander Graham Bell first filed the patent for telephone in 1876, and a year later, Bell Telephone Company was founded as a result. Later on, this Bell Telephone Company was acquired by the American Telephone and Telegraphy Company, which is the AT&T company, and this was also born out of the Bell Company. And in 1896, the Western Electric, which was the manufacturing unit of Bell Company, moved to Manhattan, and this was the home of Bell Labs till 1966, right? And the same, AT&T company, as I told you about, had a natural monopoly in the telephonic industry. This was also recognized by the US Senate, and because of the same, it was exempted from antitrust laws in 1921, right? So it had a natural monopoly, and it had a clear goal of maintaining this natural monopoly for a long time. And another clear vision was that to offer universal connectivity to all its customers. So since AT&T had a very well-defined long-term goal, the company hugely invested in research and development, and by doing so, it planned ahead in decades instead of just years. And since it already had a natural monopoly, thanks to its monopoly, it got government funding for the same. And in January 1925, Bell Labs was founded with its roots in the telephonic industry, and it was founded with the intention of consolidating research in telecommunications, right? Which was basically what AT&T did then. So if you look at the innovation timeline from 1920s to 1930s, the critical avenue of research during this time was the fundamentals of acoustics. And Bell Labs mostly focused on innovating because there was a need to provide a clear and reliable telephone connections, and at the same time attention towards exploring fundamental areas of science increased. So researchers delved a lot into pure science research as well, apart from just telephonic communication. And in 1926, an early form of synchronous sound motion picture was developed, and there was also work on sound amplification systems so that film screenings could be catered to a large set of audiences, right? And as you can see in this picture, the Vitaphone demo was the same that was done in 1926, where a synchronous sound motion picture was demonstrated by Bell Labs. And in 1927, a team of researchers headed by Herbert Ives were successfully able to transmit 128 line images from Washington to New York. Although, like as you can see, that the quality of the image is quite low. This is a 128 line television image, and this is like the most basic quality that you could have. And although the quality is not clear, the aim here was that there was long distance transmission of this 128 line image for the first time, right? And that happened in 1927. And also during the same time, the one-time pad cipher was developed at Bell Labs, and this was later on proved to be unbreakable by Claude Shannon because it was a random cipher, and it had all the characteristics of an unbreakable cipher. It was proved to be unbreakable post World War II by Claude Shannon. And in 1929, Harry Nyquist, as many of us know, developed the basis for sampling theorem. Sampling theorem has a lot of applications today in discrete time signal processing, and even in digital signal processing. So Nyquist laid the foundation for the sampling theorem that we very commonly study today. So moving on. So moving on to the 1930s and 1940s. In 1931, the foundation for radio astronomy was laid when Carl Jansky discovered the first radio astronomical source serendipitously. Right. So basically, Carl Jansky was hired to hunt down the sources of static noise in phone calls, and with the help of a basic antenna on a merry-go-round, Jansky identified three culprits of the noise that was there. So the three culprits were nearby thunderstorms, distant thunderstorms, and the third sort of source was an unknown type of hiss sound, which came from an unknown place in the sky. So the origin behind the third reason was not known, and the third type of noise which was there, it did not always come from the same place in the sky, right? So it was naturally known that it was extraterrestrial and not from the Earth. So that was known, and also it had a maxima every 23 hours 56 minutes. So later on, this was identified to be coming from the constellation of Sagittarius, and for the first time, a radio astronomical source was discovered. And in 1937, George Tibbets, who is considered to be one of the fathers of modern digital computers, designed a relay-based adder called as the Model K. It was called the Model K because he designed it on a sketch table. And in 1938, George Tibbets built the complex number computer with other researchers at Bell Labs. And in 1940, George Tibbets, he made use of a teletype to send commands over telegraph lines to this complex number computer. And by doing so, it was the first time a computing device was used remotely. And during the same time, Hendrik Bode developed, another fascinating discovery, came up with another fascinating discovery of Bode plots, right? As electrical engineering students, this is something that we come across very frequently, and this was a very fast and intuitive way to analyze the stability of various amplifier systems, and this is very commonly used even today. And along with Harry Nyquist, Hendrik Bode also developed the theoretical basis for the stability of an amplifier system, which is also studied very commonly today. And you can look at this figure, which is basically the complex number calculator at the bottom, and the top one is basically Carl Jansky working on discovering the sources of noise in the phone calls over transatlantic boundary. So in 1931, this was Carl Jansky working here, and this image below is that of a complex number computer which was developed by George Tibbets in 1938. So coming to the 1940s, the entry of United States into World War II sort of forced a reorganization of research at Bell Labs, and most of the research resources were now dedicated or devoted to wartime efforts around military electronics. And in early 1940s, a photovoltaic cell was developed at Bell Labs, and during World War II, after Pearl Harbor, Bell Labs took on nearly 1,000 different projects for the military, ranging from tank radio sets to communication systems for pilots, and also to enciphering machines which were used for scrambling secret messages. And this was very often worked upon by Turing and Shannon. And during the same time, the first encrypted communication systems, 6 was also developed. So 6 enabled US President Franklin Roosevelt and British Prime Minister Winston Churchill to have regular telephonic conversations across the Atlantic, and it was hence quite helpful for communication. And the Bell Labs also doubled its size from 4,600 to 9,200. And as a result of this, there was a lot of work on radar technology. And scientists who often worked on radar believe that whoever won the radar won the war, right? So that was also one thing to note. And during the same time, like after the World War was ended, after the World War ended in 1945, Bell Labs formed a solid state physics group, which was led by William Shockley, and this also included two other Nobel Prize awardees, John Bardeen and Walter Brattain. And the goal of this solid state physics group was to seek an alternative to vacuum tube amplifiers, right? Because vacuum tube amplifiers weren't really, going to be in use for much longer, and they always sort of knew that they needed an alternative to this. And also during the same time, like that is in 1940s, the mathematical department at Bell Labs sort of prospered a lot. Although the mathematics department was there since quite a while, it was during this time that a lot of research was happening in mathematics, and a lot of innovations were being worked upon by the mathematics department. And even like some of the notable people in mathematics department, that is Claude Shannon, Richard Hamming, and Macmillan, called themselves the Young Turks, right? And in 1947, Hamming invented the Hamming codes for error detection and error correction by introducing something called the parity bit, and this solved a very important problem in telecommunication. And you all might have also heard of this term called Hamming window, right? So Hamming window was also a result of Hamming's research on digital filters, where he was working on developing some sort of a solution to Gibbs phenomenon. So Gibbs phenomenon is a very common problem where we find discontinuity in the Fourier series of non-continuous function. So in such cases, we always need to try and reduce the jump that is there at the points of discontinuity. So Hamming window exactly does that. And in 1947, William Shockley, also like was also the like the leading the solid state physics group at Bell Labs, developed the invented the first ever transistor, and this is probably the most important invention by Bell Labs ever since it was founded, because we all know we cannot really imagine a world today without the wide ranging applications of transistors. And in 1948, Claude Shannon published his paper called A Mathematical Theory of Communication. This was worked upon throughout the World War II, but then it actually sort of came to light in 1948, and this landmark paper that is there laid the foundation for information theory. And Claude Shannon is very commonly known as the father of information theory also. So this paper laid the foundations for information theory and a lot of work in digital communications later on. For instance, Shannon used Markov processes to model sequences of letters that appear in English text. This model is very often used nowadays also for information and document retrieval, speech recognition, and handwriting recognition. And he also published his paper on cryptography, that was a mathematical theory of cryptography, which was basically a result of his wartime project on cryptography. Right? So this was worked upon by Claude Shannon during this time. And as you can see here, this was the 6 terminal in 1943, and this, as you can see, one sec. This was Claude Shannon at work in Bell Labs during the late 1940s. That was in 1948. So moving on from 1950s to 1960s, Claude Shannon was sort of done with his work on cryptography and communication. So and now he sort of wanted a new field that he could work on. So as a result of this, what happened was Claude Shannon cobbled together telephone circuits, right? So to build a machine that could actually learn by itself. And as a result of this, Claude Shannon designed something called the Thesis. Thesis was basically a maze navigating mouse, and he also built a chess playing computer among a lot of other projects. And very commonly, like today, we know how much of a big thing artificial intelligence is, and these inventions that were there at Bell Labs by Claude Shannon are considered as a precursor to AI. Right? And many people consider this as a precursor to AI, or for the first time when AI was conceived. And in 1953, Karnoff developed K-maps, which we very commonly use in Boolean algebra. And also it's something we come across very commonly in our courses. And in 1954, the first computer was built using transistors, and this paved the way for modern computing, and this was built at Bell Labs. In 1958, for the first time describing a laser, researchers, research team headed by Arthur Schaller submitted their paper about an infrared and optical maser, right? So the question of whom to credit for the first laser is still a mystery, because although Bell Labs was granted the patent for laser during that time, there was another scientist who was also working on this, that was Gordon Gould. So Gordon Gould was also working on laser at the same time, and he also published his paper at the same time. And because Bell Labs got the patent, he sort of filed a lawsuit against Bell Labs, which was a 28-year long lawsuit. And after this, eventually he won the lawsuit. But in 1958, for the first time, a laser was described at Bell Labs, and when they sort of worked upon this paper. And in 1959, another device that we very commonly come across, the MOSFET, which today is the basic building block of many electronic devices and is the most frequently manufactured device in history till date, with over 13 sextillion units manufactured from 1960 till date was conceived, right? So 13 sextillion units is like very huge, right? It's 1.3 to 10 power 22. So the MOSFET basically laid the foundation for a lot of device, like design in, especially in digital domain today, digital as well as analog domain. And basically this was also conceived at Bell Labs in 1959. And as you can see here in the picture, 1954, this was the first ever transistor computer. And here you see a picture of a thesis, which is basically the mouse which can navigate any maze. And during this 1960s to 70s period, there was a rise in computing technologies, and there was a lot of research that was going on in software and solid state electronics, along with a gradual move towards digital communication systems as well as satellite technology. So if you look at the timeline, in 1960, the first gas laser was successfully operated, and this marked the end of a journey from maser in 1958 to the actual laser that was developed in 1960. And in 1962, Telstar 1, which was the first communication satellite, was launched into space. And this was, John Pierce's dream since a very long time, and it was realized finally in 1962. And in 1964, there was a discovery confirming the Big Bang. So Bell Labs researchers discovered cosmic background radiation for the first time. So in 1964, Bell Labs, they were conducting experiments using the Horn antenna, which was an extremely sensitive device used to detect radio waves. These radio waves were very weak, so it was very critical to eliminate all sort of noise or any sort of interference so that they could be detected. And despite taking all sorts of possible steps to eliminate interference, there was always some sort of a strange buzzing noise that was coming from all parts of the sky, like continuously. It was not like it had a period also, or it periodically oscillated. It was a continuous noise which was always persisting. And they did a range of additional testing on the equipment and removed every sort of external disturbance, but still the sound did not go away or fade away. And they ultimately determined that the noise was sort of coming from outside our galaxy. And at the same time, researchers at Princeton University were looking for a way to detect residual radiation from Big Bang, right? So the residual radiation that remained from Big Bang, they were trying to detect that. And in the end, as a coincidence, it turned out that the radiation that was detected by Bell Labs was what turned out to be a perfect match for what the researchers at Princeton University predicted. And this made history, because for the first time there was some evidence confirming the Big Bang. And for the same two scientists who were behind this won the Nobel Prize in 1978. And in 1966, OFDM, that is orthogonal frequency division multiplexing, was developed, and this is a very key method in wireless communication, and also a useful method of encoding digital data on multiple carrier frequencies. And in 1967, 463 West Street, which was the home of Bell Labs from 1925 to 1966, was sold, and they shifted to Murray Hill in New Jersey. And in 1969, there were two breakthroughs. One of them was the charge coupled device, which was a breakthrough that enabled digital imaging. I mean, today, what we make use of in DSLR cameras. And also in 1969, Dennis Ritchie and Ken Thompson created the computer operating system called Unix, right? So Unix was basically created for the support of telecommunication systems, but it was also extended to general purpose computing. So it was the first time this operating system was developed. And as you can see, this is the charge coupled device in 1974, and this was the Telstar 1, which was the first communication satellite to be launched in 1961. So if you look at 1970s to 1980s, this was a new era of microelectronics where there was more sort of focus on designing new microchips for computing functions, and also for signal processing applications. And there was a gradual shift towards computing as a part of the personal computing revolution, and like a lot of resources were poured into developing into the computing department, and a lot of research was done in computing during this period. And if you look at the timeline, in 1970, Arthur Ashkin reported optical tweezers. Basically, optical tweezers were a tightly focused beam of light which could hold microscopic particles between them in a stable state. And in 1972, C was developed, which still remains one of the most popular languages till date. And in 1980, the first single chip 32-bit microprocessor with the pipelined architecture Belmac 32 was developed. And in this, domino logic was also used for the first time to speed up the CMOS design. And there were over 150,000 transistors that were used in this. One interesting thing to note here is that there were no automated tools for electronic design back then. So every chip designer had to use colored pencils for the completion of their initial design. And although it was a painstaking process, I mean, that sort of led to a lot of innovations, and all the things that we take for granted today were very thoroughly worked upon by then, and like that is exactly why Bell Labs has this reputation. And if you look at this, this was the development of Unix NC by Dennis Ritchie, and in this was Belmac 32 placed on a US stamp, right? So this was Belmac 32, as you can see here, and the image of this is Belmac 32 placed on a US stamp. So this period, that is 1980s to 1990s, was marked by a transition from outdated analog systems to digital networks. And in 1984, there was a significant split up or reorganization of the Bell company, and this led to a lot of change later on, basically. And I mean, a lot of significant change occurred because the company was broken up into a lot of smaller firms, and the Bell system, as it was known then, no longer existed. So we'll look at this once again later on. And in 1985, the first version of C++ was released. The initial aim for this was to have the level of abstraction and sophistication which Simula had, which was basically an object-oriented model. So Bjarne Stroustrup, who was the father of C++, wanted to extend the class extensions that were there and sort of increase the sophistication and have higher abstraction in the programs that were written, while also maintaining the efficiency of C. So as a result of this, C++ was born, and the first commercial version was released in 1985. And in 1987, Arthur Ashken, as we already saw before, used optical tweezers for the first time to capture a living bacteria without harming them. So for the same, he was awarded the Nobel Prize in 2018. And in 1990s, there was the internet. So most of the research now was on high-speed digital networking, and research became focused mainly on providing instant access to voice, data, and video through wired as well as wireless networks. So the most prolific area of research during this time was high-speed digital networking. And in 1996, the AT&T that was there spun off the microelectronics and optoelectronics divisions of Bell Laboratories into a new company called the Lucent Technologies. And as you can see here, this is the picture titled "The Stretchy Genes." Was basically it captures two optical tweezers with a bead of microorganisms between them. That is, this green thread-like structure or bead-like structure that you can see is a microorganism that is trapped, and the conical structure with red cones are used to sort of indicate the optical tweezers. And here is pianist Stroustrup working on C++. And now let's look at the recipe for success. Many have wondered, as you can see in this picture, this is a long hallway in the Bell Labs. So many have wondered how did such an industrial research and development lab have such a tremendous impact on both fundamental and applied science, right? So I mean, one more question that we could also ask ourselves is, can the same be recreated today? So Mervyn Kelly's core belief back then was that basic research that was there, or basic science research, was the foundation on which all the technological advances rested, right? So there was a lot of research in pure sciences, and not just a lot of specialized commercial research that was going on. There was research without any sort of schedule or progress report, and research just happened because there was this intention to actually innovate and develop new things that could help us, I mean, that could make our lives easier. And also Kelly sort of believed that attracting the talent for such sort of a industrial research lab was not really a problem, and it was very easy to get the talent required for amazing research. But the challenge was to create the right environment for research to happen, and for the research to thrive for a long time. So Kelly believed that any distractions would make researchers lose their contact with the basics or the fundamental scientific interest, and sort of decrease their productivity in research. So because of this, he was very particular about the physical environment these bright minds would work in later on. And like Steve Jobs, a lot, decades later, Kelly had a hands-on involvement in the architectural design of Bell Labs. So for the Bell Labs building, like Kelly devised flexible modular rooms along with long corridors to accommodate offices, labs, and other sort of workspace. And this layout brought together theorists, experimentalists, and technicians together. And this policy of keeping office doors open fostered some atmosphere where there was always this free exchange of ideas. Right. So, I mean, one more question we obviously thought of is, would will we be able to sort of recreate this recipe today? Recreating this recipe will be, a huge challenge today, because although in some respects we are now better placed than Bell Labs with all the technology and diverse talent that we have, bringing everyone under one roof is a very difficult task, right? Because there's always already some trend for everyone to work remotely, and also there are a lot of divisions in big technological companies which are spread through a lot of continents. So it's very hard to bring together everyone under one roof and sort of have like make research go on as well as Bell Labs did. So having the sort of collaborative environment which Bell Labs had, in my opinion, is a phenomenal task. And I mean, moving on, as you can see, this facility which was in New Jersey is now a ghost town, because there is it has not been used for a lot of years, and it's now exactly a ghost town and not a place like it was before. And one more thing is, although like today there is a lot more diverse talent that we have, and there's a lot more technological advances than before, the freedom and time to pursue any research interest is still a luxury, right? Because a lot of research that is being done now is basically mostly aimed at commercial sort of a purpose. So unlike Bell Labs in the past, most industry labs today lack the freedom to pursue projects that are different from the near-term commercial objectives, and the resulting knowledge that is always there, or any sort of new innovation that comes out, is often kept proprietary. So this was not a case with Bell Labs, because back then it had a monopoly, and since most of the research was being done in public interest, it could not keep its knowledge proprietary. But today, since we have a competitive market, it is essential for firms to keep all their research work and whatever innovations that they make proprietary, so that they can prosper better in the competitive market than their other competitors. And although there are a lot more companies with more market capitalization today, the industrial research and development labs are not able to achieve this magnitude of success. We've already looked at one reason about the collaborative environment. There is another reason that you know our current model may not be delivering, and that is because most of the businesses that we have today are disintegrated businesses, right? So one of them is specialized in a particular mm, field, and there is another firm which is specialized in another field. So since there are a lot of disintegrated businesses, they do not have any incentive to do pure science research. Their research would mostly be in their specialized field with a commercial objective. So there is no incentive to research general purpose technologies. For example, if you want to study the success of transistor, so the transistor was not just a result of the work of a solid state physics group. It involved like a team of although there were physicists, there are also metallurgists, and there are also chemists who were involved in the development of the transistor at Bell Labs. But this is not the case with firms today. And looking at Bell Labs legacy, Bell Labs like always cared about the time and like time, space, and how people interacted with each other. So, and it believed that physical proximity was very crucial. So, because of the same, it housed physicists, electrical engineers, and a lot of other scientists and thinkers under one roof. And Bell also relied on architectural design to make people more collaborative. It had long alleyways with offices decked into the sides. So some of the hallways in the building were designed to look be so long that if you tried looking down their length at another end, it would disappearing at a vanishing point. And another famous line which is there from the book The Idea Factory is that a physicist on his way to the lunch in the cafeteria was always like a magnet rolling past iron fillings. So it was never like they were able to work in isolation. There was always some exchange of ideas. Although there was a lot of research that they did on their own, there was always this exchange of ideas which created a collaborative environment. And the long, narrow hallways that were there at Bell Labs also inspired Google to use the long, narrow tables and rounded tables in their cafes, so that strangers to the office or anyone new in the office sort of interact a bit more, sort of talk about their work more, and to sort of bring strangers in the office closer. And now looking at the fall of Bell Labs. So the fall of Bell Labs was something that, like, it was not something that was not at all foreseen, on something that was very unexpected. So AT&T, basically the company which was there, it had a natural monopoly since a very long time, and it had monopoly at the government's pleasure, and all its scientific work was being done with the understanding that it was in public interest, right? But since it was like this, it could not fully exploit all the technology that it developed. So these very advances that were there, you know or made at Bell Labs, sort of led to its demise, because other companies made use of these technologies as the time went by. And from 1949, authorities pursued a case against AT&T's Bell Labs, which ultimately resulted in the first divestiture of their non-telecom arms. And AT&T lost its monopoly in 1982 and was restructured into a number of small subsidiaries. It was very frankly the end of an era, because it was no longer the big company it was. And since there was no monopoly as well, or any funding from the government, the funding of Bell Labs started to dwindle. The courts mandated that the company should divest itself of its local telephonic operations, and these divested operations, the for local telephone exchange, became the 7 regional baby bells. And a small portion of Bell Labs, which was still researching upon the local telephone operations, was spun off as Bellcore. And as you can see here, the like financial resources were also much smaller now, right? And Bell Labs was being owned by a much smaller company in the competitive business of long distance and also local telephone exchange companies. So the financial resources were much smaller, and the research work at Bell Labs gradually contracted, especially in pure research. And in 1996, as we already saw, there was another split up, and the labs also split as well. Like the Bell Labs also split as well, where three-quarters of the staff went to Lucent Technologies, while the remainder stayed with AT&T, and this led to the formation of AT&T Labs as well. So they were also split up as well, and researchers mostly followed the business, where their work was more, had a higher support, and where their work was more acknowledged and stuff like that. So moving on, if you look at current research, there is active research done by Nokia Bell Labs. Like Bell Labs today is being owned by Nokia. So there's active research going on in 5G and 6G technologies, and some of the future 6G works include Homo augmentus. So Homo augmentus will be very useful later on, because it is like the first model of human augmentation that they are actually working on, where we might actually be able to operate any sort of device just using our subconscious self, and not necessarily having to use our hand or anything. And there's also work going on in optical sensors using 6G technologies, and advanced security mechanisms using 6G, and also working on giving the world the networking speed of a 6G network. And Nokia is also one of the leaders in 6G ecosystem, and there's active work that is going on in future autonomous systems, right? So as you can see here, like today most of the research work is being done in sort of like cognitive augmentation and artificial intelligence systems and future autonomous systems, as you can see. And if you look at this timeline that is there for Nokia, so this is basically their plan as of now. So they are planning to launch 6G commercially by 2030, and the standardization phase that is there for 6G will begin, will likely start from 2025, and it will be done by 2027 to 2028. And 5G will also be enhanced, with the release of 5G advanced in 2024, and there will be very advanced networks in 5G domain as well, with new 5G features and boosting of 5G capabilities before 6G arrives at the end of this decade. And if you can look at the references and like resources for further reading, I mainly refer to this book called The Idea Factory, Bell Labs and the Great Age of American Innovation by John Gartner. And these were the other links or sites that I refer to. So thanks a lot for joining in to the seminar.